Three NVs, and you can see some additional reflectors between those. Now, what I started off by doing was experimenting with the various different spacings that we could have. The compromise of 20 meters being understacked, 10 meters being overstacked. Then what happens if I put 20 meters to the optimum position, and then where does that leave us on 15 and 10? Well, 10 was a disaster. The front to back dropped drastically. It was more like rotating dipoles, and the angle of radiation was so high that the gain dropped off hugely. So putting extra full antennas in between those Yagis just didn't work. So I started at this point by adding reflectors. Now, as soon as I started to add reflectors in between these antennas, things started to happen. Front to back was coming back. Gain was starting to appear on the upper bands. The optimum number of elements and the positions of those elements depends on the length of the boom. But on relatively short Yagis, which we would typically have on HF, it would be maybe 1 or 2 per band. Now, the additional elements between these do need enhancing and need to be optimized, but both their position and their length need to be optimized too. Now, in order to really experiment and extend to where this could go and where this kind of optimization could take us, I chose some dual band Yagis, in this case some 6 meter and 4 meter Yagis. Now, I know you guys don't have 70 megahertz 4 meters in the US, but one of the reasons for choosing this one was that radios like ICOM's 7300 in rest of world has 70 megahertz on that. And many people that are looking to have a Yagi antenna on 6 meters want 4 meters as well. So outside of the US, a 6 and 4 dual bander is a great antenna to have. When you can now start to stack these and get much longer performance, it's great, especially when you're in confined or urban lot locations. And having just the 2 bands meant that would be easier for me to spend time optimizing these additional elements. So we take a dual band, which is pretty much very close to monoband performance. In this case, it's sort of 8.5 dB of gain on each band for those 4 elements and 20 odd dB of front to back. So very similar to the monoband OWA type example. As I mentioned, in this experiment, I wanted to be removed from any third harmonic relationships due to the fact that on a 2 meter 70 SEMS Yagi, the 2 meter elements would conduct also and then destroy the pattern on 70 SEMS anyway, so that would give false results. So this one in particular is 4 elements on each band. It's 2.1 meters, so it's about 7 feet in length. And the optimized, or the starting position for the optimization of the parasitic elements in between these Yagis was 4.2 meters, so around 14 feet. So let's have a look at what we were able to achieve and the results. This is not optimizing the spacing or shifting the spacing any wider to see what results we can get. This is just having the stacked vertical spacing fixed and then optimizing the elements that we've got between the antenna. Now, it worked out that with the positioning midway between the two is at 7 feet or thereabouts. A single Yagi produced 8.52 dBi with 20.91 dB front to back. A stacked pair of those, 11.68 and 17.34. So maybe it's a little bit overstacked because the front to back's starting to drop off. If we brought that down again, we'd get some front to back but lose a bit of gain. Now, in this case, on this particular arrangement, we've just added an extra element between those two beams, just one extra reflector. And that's made a difference to the gain, not very much in this case, because it's near optimum spacing on 6 meters of 11.76, but the front to back has increased drastically, almost 10 dB increase or so. So we've got a net increase over the single Yagi of 3.2 dB. And this is how the pattern looks between the two Yagis stacked without the reflector or the additional reflector and with the reflector. There are two overlaid plots. One is in red and one is in blue. Now the two forward gain plots is very little difference. There's no delta between the two overlays, but the front to back is obviously quite pronounced. So let's look at 70. Now bearing in mind on 70 megahertz at 4.2 meter spacing, we're quite a long way over where we need to be. So single Yagi 7.83, 21 dB front to back. A stacked pair 10.9 and 18.67 front to back. In this case, because of the amount of overstacking, there are two additional elements, a parasitic reflector and a parasitic director. Although the director, which we'll talk about in a few extra slides from here, is more in line with where the driven element sits. And that produced a marked increase in gain up to 11.63, with front to back now up to 24.72. So I think you'd probably agree that's quite a respectable level of front to back to achieve. And now the increase in gain over a single Yagi is in the order of 3.8, not 3 dB. And the overlaid patterns now, we can see a distinct differential between the blue and the red line. But what's important to note is not just has the front to back increased quite significantly, and not just has the forward gain increased, but if we look at the 3 dB lines, or the 3 dB edges, that performance is visible for the whole 3 dB forward section. So we've increased gain everywhere. So the summary of achievements on this: additional gain on both bands, similar achievements on 3 bands stacking to what we would have on 2 bands, with a huge difference in front to back, an increase in the ideal stacking distance per antenna, and the removal of the compromised spacing. And this is one important point which I want to just elaborate on a little. As my experiments have been ongoing with this and have continued to move up, I get asked often for different configurations for people to self-build or that people want to buy and install themselves. And I help people with the stations that they want to produce and build the antennas themselves too. And I mentioned earlier about the limitations that we've got with guy wires and ring rotors, meaning that often there's no ideal stacking distance for these. These antennas have got to go in these places. Now, what I've been able to establish is that when you're stuck for the stacking distances that you've got to have, you can optimize these additional elements to suit your stack. So if every band is overstacked, then you can add parasitic elements in between these Yagis to improve that performance and to suit the environment of which you've got to install those antennas. So this is just a closer look here as how the dual banders looked with the parasitic elements in between. And note that that reflected, or that reflector element for 6 meters is quite a long way forward of the others in this instance. So because in this instance these antennas are very short, that any mast that's got to come off of the main tower backwards to support those 3 elements is really very short. We're talking about 5 feet long in this instance. So no complicated mechanics to keep that extra piece up, which has given us all the extra performance. So, future developments. Well, it's led me to experiment in some other areas too. And in this particular instance, this antenna, or these antennas here, are tubular quads, and as you can see, they have a boom at the top and the bottom. Now, what I've established for experimenting with these stacked quads is that it's very nice to have a very short boom and very wide beam width. Now, with a quad, because the feed is offset, traditionally we would feed both the quads at the bottom or both the quads at the top. If we feed one at the top, the bottom antenna at the top, and the top antenna at the bottom, this increases front to side by a huge margin. We're talking of 50 dB plus suppression off of the sides. So now when we're looking at contesting and maybe roving and we're up on mountain tops and there's other stations that are doing the same on other peaks, we can suppress people very heavily off the sides but still have a huge beam width. And in this particular instance, just by adding one parasitic element between those two quads, which as you can see is it's in the middle of the antennas. It's mounted directly onto the supporting mast, and then optimizing the length of that parasitic element. Those two small quads are producing 11 dB of gain and 22 dB front to back, but that's 11 dB of very, very wide footprint. So next subject is I wanted to speak about the development of my BOLPA, or band optimized log periodic. And this was quite an enjoyable experience for me, and I wanted to communicate that and just give you a bit of an inside glimpse into my thinking and how I got to where we are with this antenna. So, band optimized log periodic array, what does that mean, and how did it came to be? This started out with one of my what-if experiments, if you like, where I was looking at log periodic arrays and thinking, well, you know, one of the properties that they're very, very wide band, or can be. So what happens if we optimize one of those for a very narrow band? What does that do to the performance? Well, in this case, I built and tested this one, which was a 3-element for 20 meters. And the boom was just 6 feet long, but 6.5 dB of forward gain and 20-odd dB front to back. So it was pretty good. And that's what it looked like. This is one of my advertising photos here, but it gives you an idea as to when you look at that being a 20-meter yagi or log, how short that boom really is. And above it, you can see the pattern. That's at 50 feet above ground, and it's showing around 12 dBi, and a fairly respectable front to back on that too. But this is direct 50 ohm feed, so there's no need for a 4-to-1 balun or anything such as that here. So what happens if I want to do this multi-band, and where would I go? How would you construct that? What I did is I took the 3-element which I've built and tested, and I scaled that for 15 and 10. And then I took those 3-element band cells, if you like, and put them on the same boom, but optimized their spacing, moved them in groups of 3 backwards and forwards from one another, until I found the best point where I could conclude performance on each band. Now, this gave me 20, 15 and 10 meters, and hey what, I've got a bonus. 12 meters fell in there as well, with a very reasonable SWR. So the only thing I was missing there was 17. Now on the illustration down here, hopefully this is visible to everyone, we have an EasyNet plot here, which shows the antenna elements as they are all set together with these band sections here. The little T marks indicate a transmission line between and joining the elements together. And then what are the pink lines that raised up are the current profiles, the current distribution through the elements. Now this particular one is in use on 20 meters, and you can clearly see that the first 3 elements on there have a lot of current in them because that's the 3 active elements on 20. But also the reflector of 15 is carrying a very small amount of current as well. So it's kind of a 3+ element on 20 meters. So what about 17? There's no 17 meters. here, and to add another 3 elements, that would start to make the antenna much longer. So I had an idea. I took one element, and I took the 3 elements for 20 meters and shifted them back on the boom. So they're now out the way. Took one element and stuck it in between the 15 and 20 meters. And then I optimized the length of that 17-meter element and the position of all of the front elements and all of the back elements as one group in each set. So all of the front elements, moving all those backwards and forwards, the 3 rear 20-meter elements backwards and forwards, until we got some performance on 17 meters with respectable SWR. And as you can see there, and it's hard for me to see on this screen too on that, but front to back is well in excess of 20 dB, and we can see that the 17-meter element has loads of current, but what we have is the front of the 3 elements for 20 meters conducting current as like a reflector would, and the rear antenna or the rear element of 15 meters acting as a director would. And I refer to some of these as reflectors and directors, and they're not because they're in a log cell, but it's a lot easier to describe what is happening here and how the antenna is working. So 15 meters got a bonus from the extra element for 17 because it gave kind of an extra reflector property. If you look at the 3 elements for 15, which are 1, 2, 3 here, the 17 meters still conducting, it's still got current within it. And because of the extra element there, this one is one of the ones that has the most gain. It's around 7.8 dB, but very high, 23, 24 dB front to back throughout the 21 megahertz band. And then on to 12. Now 12 was a bit of a bonus band, as I mentioned. There's no actual element for this band, and it's just what would be the reflector element on 10 meters, which is carrying the real current, and just a little amount of current in the end of the elements either side of that. So it's like a 1+ element on that band. But it's still got a very flat SWR, around 1.3 to 1, and very flat across that band. But a bit of a compromise in the front to back now. It's around 14 dB, but still gives very good performance on 12 meters that hasn't got any elements allocated to it at all. And then finally, when you shift on to 10 meters, we've got the 3 elements which have been allocated to 10 meters, all carrying current, plus that forward one of 15. So again, front to back comes right back in excess of 20 dB, and well above it's 6.5 dB or so of forward gain too. Now the great advantage with something like this is that we've been able to, rather than have a broad and very average performance across a given range, we still have a broadband log periodic, but now we've got band cells that have been optimized. We're getting above average performance for a log on each of the ham bands with very, very flat SWR. Individual bands are optimized once they're placed on the boom, with just the element lengths being adjusted as individual and collective elements. Now I'm going to show you a few of the photos of a commercial example of this antenna using the high gain materials, and this is one we built earlier in the year to test this. And this is kind of a hybrid of what we'd been doing and some of the early development work on this log periodic. And you'll notice on the front of that there's 2 elements which are quite distinctly smaller than the rest of them. And that was the addition of 6 meters. So we've added 6 meters to the front of the log. But in order to get as much performance as we possibly could, the 6-meter elements are traditional parasitics and open sleeve fed from the main antenna. And this is just how the antenna looks at the back, with a hairpin in place in order that all of the feed lines are grounded and connected to the boom. So in a user environment, does this thing work out? And does it produce any good results? Well, bearing in mind that we can put something like an SDR radio on this and now have 5 or 6 band slices all in operation at once. If you look at the new products of Flax, for instance, the 64 and 6600, you can have one guy using a Maestro and one guy using a radio and do SO2R, and you can have one antenna connected and perform like that. Now, one of the first guys that had this was a Swedish ham that received this through a dealer I have in Sweden, SJR Service. And this was the comments when I said to him, "How's it working out?" And he said, "My customer with the Bulper has sent me this info. 1-to-1 for the whole of 20 meters, 1-to-1 for the whole of 17 meters, 1-to-1 for the whole of 15 meters, 1.3 on 12 meters, and 1-to-1 for the whole of 10 meters. So pretty much what it said it was going to do in the model. And no need for any ATUs. And this is the Swedish guy. I omitted to get his call sign, but that's the one that he's got there that's using the twin square feed lines as the antenna support elements itself. So that's it. That's the 2 subjects covered from me. Hopefully that was of interest to some of you, and be happy to take any questions if you have them.
Yes, very nice. Thank you. Thank you very much, Justin. Justin has just introduced a whole new set of antennas through high gain, and so they're just starting to be manufactured here in the United States. So very, very proud to have you here today, and thanks very much for your presentation. Okay. Thank you, Justin. So if you've been coming to these antenna forums for the past couple of years, you know that I post the slide decks up on my website. It's www.k3lr.com, and you can see all the way back to 2004. We have archived the presentations that have been given here. So we'll get ready for our next talk, and so we get everything booted up here, and continue on. Yes. You're at the high gain booth or at the Nove booth? High gain. Okay, so if you have questions for Justin, you can go to the high gain booth and you'll be all set. And so we have space weather and amateur radio science forecasting and effects. This is her second time here at the Dayton Hamvention. Please welcome Dr. Tamitha Skov.
Thanks, Tim. Hi there. I'm going to maybe flip your field on your head a little bit so that you get kind of a different perspective of your field and maybe even a deeper appreciation is what I'm hoping. And, you know, I keep seeing this every time I come here. It's only my second time here, but I keep seeing this lamenting feeling about ham radio being kind of, is it a dying field? Is it not? There's a bunch of gray hairs here. How do we get the youth involved? The whole thing. I'm hoping to give you a little bit of hope for the future and how you can look at ham radio and how important it is and what a role it's going to play in the future. So let me get a quick show of hands. How many people know what space weather is? Fantastic. This is wonderful. I can't thank you enough. You guys are absolutely on the front lines. I call you guys field reporters because you know what's happening even before I do. You basically probe the health of the ionosphere every single day, and yes, I will talk about ionospheric propagation here. I see Don. Don, you can leave. You've already seen this talk for the Ham Nation, so. Wonderful. Okay, so I'll get started here. Let's, this will be a little, for those of you who were at Contest University, about the first quarter to half of this talk will be a bit of a review, but there is new stuff, so please stick around for the second half. I don't want you to miss out. So essentially, what is space weather? Well, it's a planet's interaction with a host star and the surrounding environment. We probably already knew that, but more generally, it occurs at planets, moons, comets, asteroids, and other celestial bodies in the universe. In our solar system, which you're going to realize pretty soon is your own backyard, we see aurora at Jupiter, Saturn, and more recently at Uranus and Mars. And effects of space weather, as well as seeing aurora, are studied at Io, Europa, Ganymede, and Titan, just to name a few. Now let me give you a little interesting hint. If you see aurora, that automatically should trigger in your mind ionosphere. And what is cool about the ionosphere? It allows for ham radio propagation. So just think about it for just a moment. We're thinking about colonizing Mars, right? The next generation is called the Mars generation. That's what they've already called themselves. I'm the X generation, but they get the cool name, the Mars generation. They're ready to go colonize Mars, and that's fantastic. But do you think there's cell phone towers there? Think there's GPS there? But what is there? An ionosphere. So what do you think people will consider when they start colonizing Mars and having remote drives with their rovers, with their manned rovers to different locations on Mars, or maybe some of these other places I'm talking about? What do you think they're going to consider for their main form of communication for remote operations? HF, right? So how can the field be dead? How can the field be dying? We have a whole new generation that's going to be exploring our solar system, and everywhere you see aurora, you have an ionosphere, and everywhere you have an ionosphere, you can have ham radio communication. Okay, so taking the field, turning it on its head. So there are 4 basic phenomena. So let's get our space weather chops up, because we're going to have to deal with this. We deal with it at Earth, we're going to have to deal with it at other planets too. So we might as well learn all about what they are so that we can tell the meteorologists when they're wrong, which happens a lot. And I need help. I'm only one person. There are 4 basic types of solar phenomena that affect Earth. One is a solar flare, and I'll play the movie. Hopefully it'll play. Please play. Is it playing? Yes. Yay, there it is, right there. I'll play it again, if it'll let me. Please play again. I'll see if I can freeze it. It may not. Come on. There we go. So I'm freezing it on a solar radio burst. Okay, this is electromagnetic radiation that is broadband, goes from X-rays all the way down through radio waves. It also gets up at 2,000 megahertz, which is where GPS functions. So GPS is affected by these, just like ham radio is affected by these. So all the kids with their little cell phones and think that, oh, I got ham radio beat. No, you don't. You have to deal with the same signal propagation issues that HF radio has to deal with. So once again, another link to the youth, okay? But solar flares travel at the speed of light. This is electromagnetic radiation. It takes 8 minutes for this type of disturbance to reach Earth, okay? When you see meteorologists say a solar flare is racing towards Earth, solar flares don't race toward Earth, they're there right like that. There's something else that races towards Earth, and that's a solar storm, also known as a coronal mass ejection. 2 totally different phenomena, okay? Right now, every single one of you knows more than any meteorologist that reports for the BBC or CNN or MSNBC or anywhere else. Here is what a coronal mass ejection looks like. You see that big loop coming off the sun? This guy right here? Really big, massive, lots of gas, except it's called a plasma because it is magnetized. We have electrons and ions. We don't have neutral gas coming off of the sun. When it goes off of the sun and into the coronagraphs, this goes about 30 solar lengths out, 30 solar radii out. You can still see that loop. Let me stop the movie so maybe we can catch it. Hopefully you guys can still see that, maybe. Little dim, but it's still that loop. That same loop that you saw here, that starts right there, extends all the way out. It continues to extend out and keep that same configuration, or at least a similar one, all the way as it propagates out to Earth. Thank goodness for that, or we scientists would be lost. That field organizes what happens. And that also tells you that that ejection, that coronal mass ejection, is magnetized. Well, the Earth is magnetized, right? That same field that you feel and you read in a compass extends out into space. So we've got like two giant fridge magnets interacting in space. We've got one sending from the sun and one that is the Earth and the Earth's shield, right? We call that the Earth's magnetosphere. Now, of course, just like fridge magnets, you can push them together and they may repel each other, or you can flip one over and they click, right? If they click, then suddenly their fields become one, and all the energy that was once in this thing now gets pumped into the Earth system. And this is, again, why meteorologists get it wrong. Not every solar storm is going to click. Some of them are going to bounce off like bumper cars. And us scientists, God love us, we haven't figured out how to predict which ones click and which ones don't yet. We know why they click. It's the field direction. But we can't predict the field direction yet just by looking at pretty pictures like this. We have to wait till one of them blows right past a spacecraft and we get what we call in situ measurements. Once we get those, we know. But the only spacecraft we have sit only about 30 to 60 minutes ahead of Earth, what we call upstream of Earth, upstream in the solar wind. So we really don't have much more than a now time, a nowcast prediction. Yeah, 30 minutes isn't going to give you much. But we do know when they come, so we can say, well, there could be a storm. But it's still difficult. At any rate, those are the ones that cause aurora. These are the ones that drive you guys crazy for days on end. The next thing is something called coronal holes, because they drive fast wind. See this dark area? Kind of hard to see, I'm sure. But that dark area is where you get fast solar wind from. You don't see it on the orange sun. You can only see it on the pink sun. You can see it a little bit on the brown sun, too. But these are, as you can tell, color-coded. The reason why they're color-coded is because they're looking at different layers of the sun. Kind of peel it like an onion. The different layers tell us different information about what's going on. Coronal holes you can't see here, but you see them in this color, and we know what fast wind comes there. Come in. These will drive just like a wave in an ocean. You get a wave going, it will push against slower water ahead of it, kind of, and it will steepen into a wave and sometimes steepen into a shock. So you can drive shock waves with the fast wind. You can drive shock waves from these things doing the same thing, pushing out fast ejections out into slow solar wind. Those shock waves will help drive radiation storms. Solar flares also launch radiation storms, and this is the mess you get when you get all of that stuff happening all at the same time. You can get a particle storm, it comes up here like this. You can get a solar flare here on the day side and particle storm down here. Red, you can tell this is a map of the world. Red is bad, right? This is the D layer of the ionosphere, and when you get particle radiation coming from all of these three phenomena, you can get a real mess. And this is why the ham bands can be tanked for a long period of time. And I'll come back to that in just a minute. I'll show you a real-time example. So what is the ionosphere? Well, the ionosphere is a charged plasma layer above the atmosphere comprised of ions and electrons. Now, this area would be neutral, but it gets photoionized by the sun. The UV rays actually do that. So obviously, the ionosphere is quote-unquote thicker on the day side than it would be on the night side, because as you take the sun away, things begin to recombine, and you get a neutral atmosphere again. And obviously, this charged nature of the ionosphere facilitates radio propagation. So let's talk a little bit more about the ionosphere. What are ionospheric layers? Why are they there? How did they happen? And how do scientists look at it? Now, I don't know if many of you have seen this type of plot before. There's got electron density down here at the bottom, and you got the day side and the night side. Because obviously in the day side, when you got sunlight, you got a lot more ionization. Night side, that ionization goes away. That source of ionization goes away. So things change, right? So here's electron density at the bottom. Here's altitude going up at the top. And you see this density line. You see the peaks? They peak at the E region, F1 and F2 region. So what's happening is that here at these peaks, you're having a maximum in terms of the production of ions. Because you have these things colliding, there's all sorts of atmospheric chemistry, atmospheric physics going on. It's totally not my field. Don't ask me specifics. I will be totally dumb. But you do get a maximum right here in the density of electrons being produced. In here, there's more recombination than there is, than there is production. But then the atmospheric chemistry changes because we have different species at different altitudes. So you get yet another peak, and the same thing again. We get kind of a more of a recombination than a production. And again, we have yet another peak as the physical mechanisms change between what is being recombined and how these processes are happening at these different altitudes. So that's why you get those different layers, is that you get a peak in the electron density at these different layers. Now, when the sun goes away at night, you suddenly, of course, one of your sources of ionization goes away. So you're going to expect things to get worse. Electron density should go down, and sure enough, it does. The F1 and F2 layers actually collapse and become a single F layer, and the E layer all but disappears, as well as the D layer. But you do have a little bit of sporadic E because you do get a little bit of a peak there. Again, the specifics of those production mechanisms is not my area, so it's unfortunately not my area of specialty, so I can't answer that, but I can refer you to the people who can. So if you do have questions, don't be shy. So why do the layers change? Well, sunrise, sunset. Are you in the sun or are you not in the sun? Here's a way of looking at the globe and the way of thinking about ionospheric layers that I don't really see a lot in textbooks. Obviously, the sun is coming from this side. This is the day side. This is the night side. And you've got your F1, F2, and the E and the D layers all labeled right here. But as you begin to get to the terminators, things begin to change. You know, we always talk about the gray line, right? Why do we call it a line? It's not really a line. You ever heard the phrase of, ever want to see the sunset twice in one day? Climb a mountain? Right? Because you can see it on the ground, the sun goes down, then you climb a mountain, you get up to the top and you can watch the sun set again. Because the higher you go, the longer the sun, the more you can see the sun. Well, it's exactly the same thing with the altitude of the atmosphere. You're down near the surface, the sun will set sooner. You go higher in altitude, you can see the sun for a longer period of time because the Earth isn't occulting the sun. So these regions don't collapse all at once. They collapse in a slow progression. The D goes first, then the E, then the Fs. So you actually can get past what the Earth, the surface, people on the surface think is the terminator. You can get past it by a few hours before you actually have the F layer collapsing. So it smears out this gray line. It's not a line anymore, it's a fuzz. It's a wuzzy line, as the British say. And it happens on both sides. But you get a single F region at night and the D and E layers collapse, except you maybe have some sporadic E. So what does that mean? Well, it really means you need to think about the ionosphere, and when you're doing ham radio, not in just a single ionosphere, not even just a day and a nighttime ionosphere, but in 3 separate regions. Are you working the day? Are you working the night? Or are you working the gray? So here's a neat little picture I lifted from the late Leith Jennings, who has done some really amazing presentations. I'm sorry he's no longer with us. But I borrowed this chart because it was a really neat, simplified way of looking at the ionosphere in these 3 different regions and calling them really regions. So we have the F layer. Now, granted, during the daytime, it's F1 and 2. He simplified it a lot. But then it collapses in the gray line. And look how rapidly things are changing, really rapidly. And it becomes a single line at night that's a lot lower in altitude. Or a little bit lower in altitude. And he's got it according to skip frequency. But the E layer, of course, does the same thing, but it actually collapses a little bit sooner. And it goes down to basically nothing. And of course, the D layer collapses really early. As soon as the sun goes down, it's gone. But look what it does with propagation, right? You got 60, 80, and 160 going up to the D layer. You got 30 and 40 meters going up to your E layer, and 10 to 20 meters up to the F layer, right? But as you go through the gray line, things rapidly change. And this is why the magic happens, is because you're getting so much rapid change that you don't really know what you're going to get, and really interesting types of propagation can occur. And then, of course, at nighttime, now you're sitting basically with a single F layer, and so you're having a different altitude and a different skip frequency for your different frequencies compared to the day and compared to the gray line. So if you think about it from those terms, it makes it a little bit easier. Now, of course, I'm going to go muck that beautiful picture all up. Because when you add not just what we call the diurnal variation, but now you add space weather effects, and you add neutral atmosphere effects, suddenly those pretty smooth curves they show when they show the ionosphere, they show nice, long, smooth lines. They're not smooth. They're wavy. And space weather really makes it even wavier and even more convoluted. You get things like atmospheric heating instabilities that come up from the neutral atmosphere. These cause plasma bubbles. So you get all these weird kind of things going that change and lift up the different layers, raise them in certain places, drop them in others. You can have waves in neutral and charged regions. We have neutral winds that come in and interact with the way that the ionosphere is charged. You can have currents in the charged regions. That's like aurora. And you can have all sorts of types of things. Things begin to happen, like signal scintillation, we'll get to in a second. You can also have, of course, signal refraction. Now, this is the same thing, of course, as sticking a pencil in water and seeing the pencil bend. This is what you share with GPS, by the way. You guys get this kind of thing, and you guys love it a lot of times because for comms, it'll really help you at times or give you some really surprising contacts. But for GPS, it's a nightmare. Because all those algorithms that use GPS or GNSS, they're expecting a straight signal. From here to the satellite, it's a straight line. But if they get a bent signal like this, then the satellite they thought was over there is suddenly over here, which means where they think they are, they're here. No, they're actually way over there. And I was telling the Contest University folks, I actually have proof now because there was an Airbus operator in Scotland who actually saved his telemetry from his drone because he's a hobbyist with drones. And he had, during the Mother's Day storm last year, he had his drone doing what we call fish bowling. It was just doing this back and forth. If you can imagine 30 feet across and 18 to 20 feet high. This is what it was doing. And when we looked at the telemetry, which he shared with me, the telemetry showed this drone locking on satellites and then losing the lock, and then locking on satellites over here and losing the lock, and then locking back on those again and losing it. And so it's causing it to try to reorient itself according to what those satellites that he was triangulating his position, they were all each telling him. And that's why this thing was going back and forth like in a big banana motion. Now that's fine, it's kind of cute and fun, except when you think of Amazon Air, right? Did you know Amazon Air has a factory that's about 30 miles away from where this guy lived in Scotland? That's where their drone facility is, and they are actively dropping packages in test runs. As a matter of fact, the BBC, just a few weeks prior to this, to me coming to England to see all this stuff happening and getting these reports, the Amazon Air had just dropped a package that had like a movie and a bag of popcorn in some guy's backyard. This was a test run and a success run. And this is, like I said, 30 miles away from this fish. I don't know about you. Do you want an Amazon Air drone to be doing this in your backyard? No. So you guys are already more aware than Amazon Air. I mean, it's a huge company, global company, right? You guys already know more about their signal propagation and the effects of the signal propagation simply because of the field that you're in. And again, this is becoming more and more relevant every single day. So when I hear all these groans about ham radio being a dying field, I'm like, no, not even. You guys are more relevant now than you've ever been. So one other thing I want to talk about is signal scintillation. This is most likely what was happening for that drone. It happens under aurora all the time with GPS. It happens to you guys. And if you ever wonder, scintillation, it's a big word. It's kind of hard to explain, but really it's not. Because you guys see scintillation every time you look up at the night sky. The twinkle, twinkle, little star, right? That's visual scintillation. Those light waves are just kind of scattering around, and that's why you see it get brighter and darker and brighter and dimmer and all this kind of stuff. Color kind of changes. That's exactly what twinkle, twinkle, little star is. But on ham radio, you hear it. The signal fades, it comes back, you get comb filtering, you get all of these weird different effects. Just so next time you hear all that kind of stuff, just sing to yourself, twinkle, twinkle, little star. So keeping all of that in mind, let's talk a little bit. I'm going to give you an example of how the ionosphere is affected during a typical solar storm. You don't need to look at all this stuff. This is data from the Space Weather Prediction Center. But what I do want to show you is that this is a radiation storm. There's two of them, 1, 2. You can see where the data goes up. This is 1, kind of 2, 3 big solar flares. So an X-class flare and an M8.7, so almost an X-class flare in itself. This data is only a week long. And we had 2 radio blackouts, 2 radiation storms, and a geomagnetic storm that all ensued within this week. And this is the bad thing about space weather, is that what happens is that you typically get a sunspot on the sun that's angry. It's just mad. So it comes into Earth view and it just spits, and it fires off a storm, and it fires off a flare, and it keeps rotating, and it's still mad, and it keeps firing more and more and more and more until it rotates out of view. And that takes about 2 weeks. So that's exactly what this is. It's just a single sunspot that hates life, really is dejected. Its therapy isn't working. It's just very angry. And so it just gives us a fit until it rotates out of view. So what happens is that the ionosphere doesn't just get hit. It gets hit and it gets hit again, and it's it's like George Foreman, right? It's you're getting pummeled from all sides. So that's the kind of thing that we have to deal with. And that's what you see here. This is the DRAP version. So this is the D layer of the ionosphere during that period of time I showed you. This is during one of those flares. This was local noon. So this is when the solar flare is happening, and you're seeing all of this red. And I've already mentioned red is bad, right? But I'll show you a more interesting region in a second. So you can see we've got a lot of absorption. The radiation storm is just starting, so you can see at both poles. You got a lot of that stuff. But here's the cool thing. Remember we talked about the terminator? We talked about the gray line being kind of a gray region? Right. What do you think this is? Does it look kind of like something that's changing fast? Right? What you look for are rainbow colors. And it's not just the 60s, man. Rainbow is cool because here, this is where the magic happens. This is where you can get really great contacts. This is where you can get propagation that you never expected to get. And it's once again all because you're getting changes in the ionosphere that are very, very fast. So yeah, red is bad. You won't get anything but noise and hiss. But look at the colors next time you look at these maps, and look at the opportunity, because you really can get some. Okay. Oh, by the way, I forgot to mention, during this period of time, this is the January 27th, the FAA, and I mentioned this at Contest University, the FAA had a report from their Central West Pacific and the Central East Pacific. They had 13 overdue position reports. Does anybody have an idea what that means? They lost 13 airplanes. No communications, period. They lost it for about half an hour, from what I've been told. And this happens a lot. Anytime you get, I hope that's a June bug and not a bee. Anytime they get big solar flares and when you get radiation storms. This radiation storm, when it actually got to full force, this thing caused a major airline to lose 3 sets of polar flights over about 3 or 4 days. So the FAA knows about this stuff, and they have to deal with it all the time. And once again, it's because of communications. Once again, these are communications on HF radio, or HF, typically HF. And I'm not even going to go into the bigger storms. That was just a typical storm series. So let me quickly talk about solar variability. This is some of the stuff that I did not talk about at Contest University as well, so I didn't get a chance to. So the sun's activity cycle has about about 11-year periodicity. Because the sun's magnetic field is constantly reversing. The sun is basically a big lava lamp, and it's always moving. The activity will increase for a few years surrounding the solar maximum. You can see here's 1996 solar minimum. You can see the sun's pretty quiet. And you go here to about 2001 near solar max. It's pretty bright. And then it goes here to about 2006 again, and it's almost just like it was. So this is about 11 years. So this is 10 years here. But it's about 11 years for a typical solar cycle. But the thing is that there's other competing cycles. I mean, there's half a dozen different names. I won't bother with the names here. But they cause deviations from the 11-year cycle. You can get ones that are about even 14 years. Typically, the more active the cycle is, the shorter the duration, the lower the amplitude of the cycle, lower activity, the longer duration. And you know, we've been trying to watch these things over, as you can see, a long period of time. That's kind of the average activity. We had a Dalton minimum back here. This is when the River Thames froze. The Maunder is when we had no sunspots at all, but you know, that's we're not going into that. Some people used to think we were. We think we're pretty much right here, and I'll talk about that in a second. But we can use sunspots as a proxy for solar activity. We've been doing that for quite some time. So where are we now? Well, recent cycles are showing dramatic changes, which are making predictions more complicated. The consensus, as much as the solar scientists can be in a consensus, is that we're in like a Dalton-like minimum. Okay, the cycle is slower because there's less activity. It's up to about 14 years-ish, give or take an ish. There's lower luminosity. We have slower currents of plasma underneath the sun's surface. There's lower magnetic field strength. Magnetic field strength is also a proxy for solar flux. So you never like to see that, right? Lower activity at maximum. The solar maximum has been double peaked. There was a first peak in 2011 and 12, and then the second is in 2014 to 2015. And you can see down here, I'm showing the different, this is how hard we struggled as solar physicists. We struggled trying to get these predictions correct. Back in 2008, we predicted that we'd have a solar max in 2012, and it would be about 150 sunspots. You know, at max, maybe a little bit lighter, maybe 125. In 2009, we made another prediction. We revised it, brought the solar max to 2013. And then in April 2011, you can see we shrunk it even further. 2013 and a half, we kept pushing that solar maximum to the right. In the end, this is what it looked like, and it is on the same scale. So our middle prediction from 2009 was about right for amplitude, but way off when it came to solar max. So basically, none of our predictions were right, no matter how many times we revised them. The solar max was about 2014, and now we're on our way down to solar minimum. But let me show you something very interesting. And once again, we don't have enough statistics to really be able to make historical data work for us. You know, they always say in the stock market, past performance is not a guarantee of future results. Yeah, well, you apply it to the sun too. Currently, we're nearing the end of the declining phase of the solar cycle. This is where we were back in 2013. You can see sunspots and a lot of brightness. This is where we are now. I took these shots away off the web about 11th of May. And this, by the way, after this weekend, the sun's going to look like this again. Kind of dull and boring, so I apologize. Probably a spotless sun. There's less solar storms due to fast solar wind from coronal holes. We're having less chances for ionization of the ionosphere due to some of these solar storms. We're not even getting solar storms from eruptions because we're not really getting many CMEs. So everything is really beginning to quiet down. The average solar flux is getting very low due to the increasing number of spotless days just like this, okay? But, getting closer to solar minimum brings new opportunities. We're kind of, solar physicists, and I'm actually not one, it's part of my community. I actually am a heliospheric physicist, but these guys are really dear to my heart. So they're kind of like baseball statisticians. You know, when you play baseball, they do statistics on everything. I mean, everything. How many times the guy pulls up his socks, how many times he spits, right? I mean, it's insane. Well, solar physicists are kind of like that. Spotless days. If we don't have sunspots, let's count how many days we don't have sunspots, and let's see what we can do with that information. Believe it or not, there's information that's valuable in there, and we're seeing something very intriguing. Got this plot down here, and what we've looked at is that the spotless days can actually be used as a predictor, potentially, of future activity. If we compare the number of spotless days to previous cycles that had X number of spotless days. And that's what this plot is down here. And I want you to concentrate on the blue and the red line. This plot is the average number of spotless days going up. And this is the month since the 10th spotless day. So basically time going bigger that way. And with the blue line, this is an average of cycles, solar cycle 10 through 15 and solar cycle 24, which is the one we were just in. These are the slow, these are the slow cycles. So you can see the blue line ramps up kind of slow. So the amount of time it takes to get a spotless day and then keep those spotless days, it's slow. It doesn't happen very fast. But once you start getting spotless days, the total number of spotless days is quite high. Well, that makes sense. Less activity. It may take it longer to kind of get its motor running to actually just get you to these spotless days. But once you get the spotless days, it's lasting forever, right? Because these cycles are really boring. The red line shows the faster cycles, the more active cycles. Well, they ramp up quite quickly. So you get to spotless days, you get a lot of spotless days really fast. You know, this motor's running, okay? It's ready to go. So it's going to go through its solar minimum and get through and get out the other side as fast as it can. So it ramps up quickly, but then the total number of days that are spotless actually is quite lower, which makes sense because the active cycles the active cycles are shorter. So it kind of runs through its cycle faster. Now here, this area in here is what I've blown up in this portion here. Hopefully you can see it. The green line is where we are now. Now remember, the blue are the slow ones, the low active cycles, right? These are the cycles that are very, very low in activity and the ones that you ham radio operators hate. The red ones are the more active ones, the ones that give you a decent solar flux and, you know, we get some decent activity. And look at where the green line is trending. Does anybody see that? It's not trending where the blue is. If anything, it's trending faster than the red. The red ones are the active cycles. Now, it's way too soon to judge. But it's a very interesting thing. It's raising some eyebrows in the solar physics community saying, well, wait a minute, we thought the sun was going to sleep. Is the sun showing signs of life? Might it actually be coming back? Too soon to tell. But it sure kind of, I don't know if it like you, but it tickles my funny bone a little bit. So, you know, sing your sun god chant. Rah, rah, sunspot. We want more spotless days. The more spotless days we get, the faster we get back. So where are we? That's talking about space weather forecasting. There was a little bit there. Where are we? You'd think that with everything that we've got, you know, we've got these space weather prediction centers all over the world. They're developed mainly as a response to superstorms. We have models that predict solar fields, CME transit, magnetospheric responses, solar storm alerts, radio blackouts, solar radiation storms. We have FAA alerts, space and ground telescopes. We monitor the sun 24/7. Even the backside of the sun we monitor. We have spaceship Earth networks for cosmic rays. My gosh, we've got everything covered, right? Not even close. There are so many things we can't see. We have spacecraft that are so far out there that it takes us minutes and minutes and minutes just to even get data, sometimes hours to get data. And the amount of data we get is like sucking through the smallest coffee straw. We can't pull down that kind of data that we need, not like we can do with Earth orbiting satellites. So we are starved for data, for the amount of data that we can do. Plus, we don't have the processing power to be able to put models into place that have all the physics that we need. So we're really back to kind of like being in the 60s. Remember terrestrial weather when there was nothing but tornado sirens? Anybody remember that? Well, Harry Volkmann was a man who used to, what they call pinch, the military tornado forecasts right off the military bases. And he began to broadcast them to the public back in the 50s to the 60s. That's when it really began to take off. And he got tons of people saying, thank you, thank you, thank you for doing what you do. And the military was saying, no, 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 you'll incite a panic. But it didn't. Well, this is exactly where we are today. I hate to say it, I really do. I think I'm the only one doing this. And I'm taking the data straight from NOAA, straight from you know, the Space Weather Prediction Center that serves the public, yes, but its main customers are the military and government agencies. They would love to serve you more, but they really can't. They're kind of hamstrung in delivering the types of data products that they deliver because those are their primary customers as of yet. But what we're doing is trying to change all that. We're trying to create something where we can actually have space weather broadcasts be part of terrestrial meteorology. We may have to have space AccuWeather soon, is what we're thinking of. So that's what we're doing, and what's cool about that is that it means that the field is completely wide open. There's a lot to do, there's a lot to understand. We don't have a lot of real-time, you know, nowcasting of the ionosphere. So again, you guys are on the front lines. You deal with space weather every single day. And so this kind of thing is becoming more and more relevant. And that's just here at Earth. Remember the Mars generation. So here's an example of how you're relevant. We have this eclipse. I'm sure you guys have heard of HamSci. They've got a forum, you know, tomorrow in room 4, I think, in the morning. And this is the first eclipse that's going to cross the entire continental USA in the past 100 years. And the cool thing is that there's a lot of ionospheric science that needs to happen. This 90-minute eclipse will change the conductivity in the ionosphere and affect radio propagation. I think the eclipse has shadow effects, and it actually, the shadow is actually propagating in the co-rotating frame with the Earth instead of being where the terminator is. So it kind of affects the ionosphere differently. And I think they've already confirmed that the D and E regions do collapse when the shadow goes over, but how the F region responds is very controversial. So there's a lot of work to be done here, and we can learn a lot about how basically a moving gray line can affect us. So we're learning more about that gray region by doing this type of stuff. And it's all ham radio. This is all stuff that you guys can use to contribute. So if you want to know anything more about the study, please go to hamsci.org. But this is the type of thing that's going to start picking up and become more and more important as time goes on. Because basically our future does rely on space weather. And I think this community and the space weather community, we really have kind of a, there's a lot of synergy here, and we can really help each other's causes. We have, because reliance on space is advancing, we have wireless technologies. Did you know there's 6 billion people in the world today that have cell phones? That's more people that have cell phones than have toilets. And if you don't believe me, I'll show you the Time magazine article that I got that from. We have GPS receivers, or GNSS if you're European. Satellite service providers are exploding. We have self-driving cars. Google has been driving cars on California roads since 2012. I don't know where it is in the rest of the United States, but I've seen Google cars driving right next to me on the freeway. Unmanned aerial vehicles, the FAA allowed GPS and GNSS-enabled drones to share commercial airspace in 2015. This scares me to death. Google car has LiDAR. They can map the ground, but I don't know how you map the sky. So all they have working for them is collision avoidance. And that's not very much. We also have space tourism. Worldview is performing manned test flights in 2017. Do you remember when Alex Baumgartner did that Red Bull jump and skydived? Then Alan Eustace, a few months later, broke his record, like 135,000 feet. The company that took both of those guys up in the balloons, that company is now called Worldview. And unlike Virgin Galactic, that wants to give you an e-ticket ride all the way up to space for, tons and tons of money, Worldview's taking a different approach. They're going to put you in a balloon with an enclosed capsule with a bathroom and a full bar. Sounds like my kind of thing, huh? And they're going to slowly, gently lift you up with this helium balloon and take you up to 110,000 feet and let you just kind of hang there for a little bit. And then they're going to jettison that balloon, and they're going to have an astronaut with parasailing, and they're going to glide you back down. Unlike Gilligan's Island, this is a 5-hour tour. But I don't know about you, but I would love to go up in one of these balloons when there's aurora, because it may still be slightly above you at 110,000, but it'll look like it's all around you. How many people would like to see aurora like you're inside it? How many people want to go up during a radiation storm? You don't want a CAT scan? Or maybe 2 or 3? Me neither. So this is relevant, this is coming. They're doing manned test flights now with the balloons and the paragliders. And you can actually go to worldview.com and take a look. They are really working at this. So, this kind of stuff is happening. And yet, look where our meteorologists are. Look at this guy. This is BBC. Solar flare races towards Earth. 8 minutes, people, 8 minutes. Solar flares are not what races towards Earth. By the time you see a solar flare, it's already here. And what does it do to the ham bands? You guys know it before they do. What hits Earth are CMEs, yet credentialed meteorologists don't know that. They can't get the lingo straight. They don't know anything about space weather, and we've got to educate them. I will share a story. When I was over in England, in Exeter, just a few months ago, I was at basically the UK version of the Space Weather Prediction Center. I was contacted by a BBC meteorologist, David Brain. If anybody knows BBC One, this is who he works for, and he's located in Exeter, and he manages a whole bunch of meteorologists. And he contacted me and he said, what do I do? The BBC is requiring us to start working on space weather and including some of that information in our reports. I don't know who to go to. So I chatted with him, and I told him all these things that he's going to need to learn. And I said, don't worry, we're here. We'll help you. We'll help figure it out. And please contact us when you're ready. So this future is coming. And I tell you, you guys are going to be a big part of it, if you want. Okay? So thank you for being here.
Thank you, Tamitha. How many people watch Ham Nation? Hey, And you see Tamitha every week on Ham Nation. And also you see Don Wilbanks. Don, please stand up. AE5DW in the house. Okay. Radio Alpha 6 Lima Bravo Sierra, where are you? He is on his way up here. He's going to plug in his stick and we will be moving along. We have two excellent presentations to go. You can find previous talks, and all of these talks will be archived on my website, www.k3lr.com. And we've got archives all the way back to 2004, so you can see the slide decks. And increasingly, we are having YouTube videos posted from the antenna forum as well. So, let's see. Here we go. Slideshow. Oh, we're still stuck there. Shut down some of these. Is this you? Nope. How come that is not on now? No.
Well, we have to close a lot of applications. I mean, the PowerPoint applications.
Did you, Greg? Can you come up here? Got it here, but fails to.
It's the same computer, right?
Yeah.
How'd you get rid of Tamitha's slides? Because they were left up there, right? I wonder if I need to hit the source button or something, sort of resync it. That's what you said.
Yeah. All right. Okay, we will get this going momentarily. Stretch a little bit. Don't want to power off. There we go. That's what got us in trouble before. No. Slideshow. We're in the beginning. Okay. Please welcome Radio Alpha 6 Lima Bravo Sierra with multiplexer technology.
Thank you, Tim. My name is Andy, and the call is Radio Alpha 6 Lima Bravo Sugar, but most of my time I'm operating from Papa 33 Whiskey or Echo Fox 8 Radio. So, the multiplexer technology was born in 2008, for me at least, HF multiplexer technology. In that year we implemented some in-band antennas and the in-band style of operation at Papa 33 Whiskey, so I was very happy with that. And one sunny day discussing future WRTC 2010 competition in Moscow, we are thinking what can we do in order to win it in Russia by Russian teams. So, and I was suggested to bring something into the field to make it better. So of course after the in-band operation, the only thing you can do with WRTC antenna setup is to increase the usage of tri-band antenna. So the first intention was to be even by two radio on the same band, but later on we understood it's too complicated, and just 2 radios and 2 different bands is good enough, and will bring a much better QSO numbers into our logs. So the very first HF triplexer we built approximately in November 2008. It looks very different now. And what is a multiplexer? It does allow you to use tri-bander or two-band antenna by 2 or 3 radios, or even by 4 radios if it's a 4-band antenna. The only issue with a multiplex is that you cannot use it without the bandpass filter. So you must use also the bandpass filter if you want to avoid any kind of noise or QRM. The multiplexer is a filter, just a filter. As every filter, it has some good properties and some of them is bad. And the most popular question is, can I frame my radio? Yes, you can. And at the same time, it's very easy to avoid it. Just use switching lockout in order not to be on the same band, and just consider your power, choosing your triplexer and the bandpass filters. It's all easy. So, the multiplexers, now we have 4 of them. Duplexers for two bands, dual band antennas. Triplexers, quadplexers for the 4-band antennas, and even a pentaplexer for the hex beams or some multi-band vertical antennas. The specification of any plexer starts with the losses. It's just a fraction of dB, and typically it's 0.2 or something like that. And what is 0.1 dB loss? If you transmit 100 watts, then you still have 98 watts in your antenna. That's nothing. This losses is absolutely nothing. Even if you add 0.3 dB loss, it's still 93 watts. If you transmit legal power, 1.5 kilowatt, then the losses is still negligible. So the question how much the losses in your triplexer is absolutely useless. More important level, it's already something to consider. But with power losses dissipated in a few components of your triplexer, so it's not very important. But from these figures, look at the attenuation or losses of 0.5 dB. That's already 160 watts if you transmit 1,500. And this is dissipated in your bandpass filter with the losses about this figure. So this figure is already good. So the most important thing in any multiplexer is an isolation. Look at this layout. So you transmit, let's say, on 20 meters. The signal goes through to antenna. It's okay. But there are some other things, like second harmonics and other elements, some other noise, which is going into the other ports of your triplexer, into the second transceiver. So the most important thing is the isolation between the ports, not the isolation of the pass from the input to antenna output to other bands, but isolation to the other ports. That's the most important things. And now we have isolation. Let's see the typical layout of 14 to 15 meters, 14 to 21, sorry. That's the figures from minus 33 to minus 43 dB. And on 21, it's minus 30 to minus 46 dB. So the isolation between 2 outputs, 20 meters and 15 meters, is around 30 to 40 dB. That's a very good figure now. On 10 meters, about the same. From 20 to 10, it's again about 33 to 39 or something like that. So let's fix it at 35. What does this mean? Again, if you transmit 100 watts, you will have at the output of your triplexer at 15 meters of 0.1 watts. And if you transmit 1.5 kilowatt, then the output will be at 1.5 watt. And this figure already dangerous to your receiver or transceiver, whatever. It clearly shows that you must use a bandpass filter. So, again, the issue with isolation is safety of your radios and interference. The starting figures probably is around plus 10 dBm, and we know some cases where the only one triplexer was used by a team in WRTC with K3 radio, and K3 is very clean radio, and they was happy with that. The triplexer was about minus 35 dB. At the same time, at the same WRTC, another team with a system of triplexer and filters with about minus 85 to 90 dB isolation still had some QRM and problems because of the problem, as later was discovered, with one of the connectors. So you have a good system. Minus 80 to 90 dB isolation is very high figure, but you still have a problem because of one connector. So be careful with that. And what does mean a trouble-free operation? Let's think the WRTC, let's look at the WRTC example. You have just two transceivers, both of them 100 watts. That's absolutely nothing. But now we use this technology on a multi-single station with a legal power, and you know in Europe the legal power means a little bit different things, and they are running 2 or 3 transmitters at the same time. With a quadplexer, up to 3 stations could be at the same time. So the total amount of QRM from other transmitters is double compared to the WRTC situation. So, and what does mean QRM free operation? Is it harmonic levels? No. Harmonic is nothing. Just S9 plus maybe 5 to 10 dB and just a few KC, maybe 1 or 2 or so on a clean radio. The only real indicator is that no other signs of station transmission you can hear on a second radio is yes. That's the thing we have to do. So there's also some different things when we are speaking about 10 meters and let's say 80 meters. This is not the WRTC case, but again we are speaking about modern usage of triplexers. On 10 meters, observation. If you are building the system for someone with some different radios, right now it could be K3, but later on it could be some other radios. The system should be at minus 80 or maybe 90 dB, but it's better to have it closer to 100 dB. And again, the triplex alone cannot do it. The filters which was available in 2008 when we started to build the systems was not even close to that figures. So we decided to use very good and famous W3NQN filters, just modify them a bit and adding some rejection sections to the nearby bands and some other bands in order to get these very tall requirements. So now, let's look at the figure. The triplexer, the version of triplexer of 2008, by the way, it's a little bit different from today's version. With W3NQN bandpass filter, 20 to 15 meter band isolation was at 57 dB and 62 dB. That's not so bad. But when they modified the bandpass filters only, they got isolation of 96 and 103 dB. This is the isolation which was measured by professional equipment on a triplexer with 2 bandpass filters without any switching. This is a very important statement, I would say, without switching. So now let's see what's going on later. By the way, today we have 1.5 kilowatt devices, triplex and Perfobox filters, and the isolation is still minus 94 and minus 88 dB. With the high power bandpass filters and triplexes, it's a little bit more tricky to get good isolation, but we're still close to the target figures of minus 90. Very good picture. Isolation from 4 to 15, which was boring me very low at Papa 33 Whiskey, now is at minus 100 dB. It's a very good figure. Minus 100 dB is isolation of the cables, by the way. So, cables. In general, they are good enough. We have a shielding effectiveness from, let's say, Andrew had stated as more than 90 dB. Messi and Paoloni, which is famous in Europe, about 100 dB, and it's good enough. But again, about connectors. If one of them is not soldered, what does mean soldered? The braid of the coax cable should be soldered. The connector should be clean. Otherwise, you can get extra up to maybe 1 dB of losses, just in the dirty connectors. So it's very important to have a good and clean connectors. The switches. In 2008, we had 3 available switches. The KK1L, which I might try to call entry-level switch. Then RK226. And about 60, 65 dB on 10 meters. That's good figures. That's a good switch, but not for this task. The RK226 switch, which is different from KK1L and Array Solutions and some others by having extra relay in the pass to second radio, is much more isolation. It's minus 90 on 160 and 80 on 10 meters. But the matrix switches, if you test them, then isolation is minus 125 on 160 and about minus 95 on 10 meters. But later we made some improvements to these switches on 10 meters and got a little bit more figures on 10 meters. How does it look? Everyone knows what is a 6-pack, what is KK1L, but matrix switch is also should be known to everyone. It's just a couple of switches. Pretty simple one, 1x2, and some 1x6. Isolation in each of them is about, let's say, 60 dB. So the total isolation from the input number 1, the signal is going to the switch number 2, and goes to antenna. But there is also some other pass to the switch number 2, which is goes to second radio. So, and this red line, it shows the pass for the isolation figures. And again, at minus 60 dB or something like that in the second switch, in total, for more than, let's say, 2K or 3K, but with matrix switches you can do anything, just in case you need it. The isolation figures, again, in matrix switches is minus 128 on 160 and minus 93 dB on 10. So, the combination of multiplexer, filter, and relay switch, typically it looks like this, the most simple layout. The triplex itself, 3-band pass filters, and some kind of 2x6 switch. Actually, what I was thinking first, and most of my friends at least, that the signal is going to antenna and that's it. But actually not. The signal is going back to the second radio. But unfortunately, the signal is not going through the bandpass filter into triplexer and then back to via the second bandpass filter into the switch. That's wrong. Actually, the signal is going directly in the switch. The second harmonics and all other dirty sheets is going to, sorry about that, into second output of the switch direct. Minus 62 and minus 56. If you remember, the isolation of the filter and triplexer was 20 dB more. So we lost all the insulation inside the relay switch. If you will change the switch to the, let's say, RK226, the isolation now is at minus 84. That's good. With a matrix switch, isolation is again more than 100 dB. But the best place and the best layout, which ensures you to get the best and then triplexer. In this case, the isolation is actually minus 116 and minus 128 on 10 meters. And it doesn't change in significant figures when changing from KK1L to matrix switch or any other one, because it's obvious. You have a filter first. All that harmonics, let's say, is already filtered out of the switch. Then again, you have some isolation in the switch. So this is the best layout for anything that requires good isolation. And summarizing a bit, the triplexer, isolation, 40 to 34, with the filters, 100 to 120. The switch itself, 64 to 85, 77 to 83, 100 to 110, and a complete system can vary from minus 62 to minus 120. So, about antennas. It could be some simple, let's say, inverted V antenna, fit with a single core. Upside down. Yes, we can do upside down. For in-band remote sites, with a hard line and installation time saving solutions. This is probably the most extreme case, but let's see. You can connect two single band antennas to the inputs of duplexer. So now you can connect just one coax cable and transmit either on 160 or 80 meters, and your signal will go through the duplexer to antenna. You don't need any switch. You can Why do you need it? Let's take as an example Echo Fox 8 radio. We have two in-band sites for two in-band stations. which is about 350 meters away. 350 meters, that's 1,000 feet of coax cable. The losses. So we use a hard line. Believe me, it's a hard job to unroll with cable before every contest and unroll it after the contest. So that's smart. Antennas with these plexus by 2 radios, by 3 radios, by 4 radios on different bands. Actually, we need only 2, one run band and one multiplier band. But anyhow, this is a way to do it. And receive only. Yes, we can use it on receive. Let's compare first. Let's think. Minus 9.5 in a 6 to 8 weight splitters. At our station, I mean Russian station on Cyprus and Gran Canaria and Morocco, we use up to 6 or 7 stations on a band. So the losses of minus 10 dB it's a loss only in the splitters. Don't forget about cables. The receive cables to the receive side is also 300 meters, 1,000 feet with maybe 5 to 6 dB losses on 80. So the total losses is too high. And again, and one of them at minus 3. That's good. Minus 3 and minus 6 is nothing. That's only 3 radios. But for multi-multi, for the real boys, well, we need 3 stations at least on 4. Then we use a wideband splitter, which is connected to the output number 1, which is 160. So after 160 output, we connect it to 1x3 wideband splitter, and all of them is connected to the antenna switch, which could be anyone. Of course, a large number of stations is only Russian way to play a game. That's true. So the expedition layout and benefits of using quadplexes. The expedition is almost the same as our contest petition, like Papa 33 Whiskey and Echo Fox 8 Radio and CN2A. We go just 2 weeks before, we build a station, we dismantle everything. So the amount of labor should be as low as low. One 60-meter switch into the quadplexer back. And then using a single coax cable and a quadplexer in a tent. Now you can use one single cable. You can use 3 stations, 1, 60, 80, and 40. And Ethernet cable, any quality, with a single coax line of good quality, and it's very easy solution. So the benefits of using the multiplexer technology.
Thank you, Andy. Your stick, Andy. Yes. Okay. So we have a very, very nice presentation coming up here on a very large,
Is WB9Z here? He's not. Well, when I was very young, I was a dreamer all my life. It's a little section about my dreaming. Oop. I have 4 daughters, and they're all supportive of my hobby, and my wife is my winch wench, and she's a radio amateur but hardly makes any contacts at all. Last Saturday was the Kentucky Derby, and you know who won? Always Dreaming, right? Yes, and I thought very appropriate, and I'm always dreaming. From the time I was just a little boy, I was dreaming. I started way back in 1949, which means I've been a radio amateur more than 35 years. And my first transmitter was just a little 6L6 on 40 meters, 70-70, and I ran the plate cherry red thinking that was high power. Little did I know it was maybe 1 watt out. My first contact was G8KP, and it was just a little dipole. Over the years, things changed. This is how I looked when I was, I'm 13 or 14 years old, and my mother buys me a radio which costs $39.50, and that was my first tester. And I collected cigar boxes. I have never smoked a cigar in my life, but I have probably 50 cigar boxes over the years, and I have nuts and bolts and all sorts of things in there. That was my, back one. When I was a sophomore in high school, I bought this 65-foot tower. My brother and I took it down. We had no special tools, we had no good ropes, but we got it down. Amazing. I wish I had kept it because it was a good blade, a good gearbox, but I wanted the tower, $35. And Leo Meyerson had, any of you remember Leo Meyerson, W0ZSQ? Well, I wanted a highlight beam. It cost $64.50. And I talked to him, and he said, how much money do you have? I think I put $20 down. And he talked to my father, who was a minister, and he was convinced that I'd probably pay it off, and he did. I've tracked him over the years. Years later, I talked to him about that. He said, in today's world, I would never do that. Things have changed. Dick Airhorn wanted my tower that I had taken down, and I shipped it out to him in California, and he gave me a SB-10, and that was the beginning of my sideband effort. But he also talked me into buying a Triax rotating tower, a crank-up tower. And it was a good tower. I had an anemometer on it. It would go down halfway in the wind, but one day I was working on it. I didn't turn the anemometer back on. The tower went down. The mast went through a boat next door. When the paper wrote it up, it sounded like it went through the deck of the Queen Mary, but it was probably a $200 fishing boat. At that point, I thought, someday I'm going to own a piece of land where if anything falls down, it's on my property. And this is what I bought. Over the years, I've been very fortunate because in my mind, I've lived the best time in America. And the translation of that is, from the earliest years, I was a scrounger. And I could go to junkyards, and the people knew I collected bearings, and they would put bearings aside, and when I'd come in, I'd buy them for whatever junk value. And I probably have 60 bearings, anywhere from 10 inches down to 1.5 inches. You can't beat that per price. And the power company would let me scrounge through their boxes, and that's a nice roller. There's another one over there. I can crank up my 1,200 feet. I have seven beverages on 160 meters, and I wind them up on that, and then I can pull them out. I mark them. I'm very lucky. That cost me nothing except the work of getting it unstuck and painting it, and I have a lot of tools. And some of the amateurs will inherit the tools because at my age, 42 times 2 plus 1, I won't live forever. But at any rate, I have a lot of tools. Then I had always dreamed of a big beam, a 40-meter beam, which I have, 2 high gains, the commercial ones, 403Bs. But I really wanted an 80-meter beam. And WB9Z had an M2 that had fallen apart. He said, Paul, you can have it. But I never went to get it, and he still has it. It's in his bone pile. But I thought, when I was in Friedmanhofe last year, I thought, OptiBeam. So I bought an OptiBeam. And that's some of the aluminum I have in my pole shed and towers. I probably have 1,000 feet of towers on the ground, different kinds of things. Well, the OptiBeam came, and some of my radio friends came over to help me unpack it, and it was packed so well, it could have gone to Mars and back and been in good shape. But when I looked at the elements, I thought, I'm not sure about this. And I looked at the boom, I thought, no way. It was such a small boom. And then I heard from some W5s that the elements are falling apart. The elements are metric, and I have a lot of aluminum, but it won't fit metric. And I probably have 500 pounds of steel bolts, from 172s to 1-inch bolts, lots of bolts. But if I lose a metric nut, I'm out of business. So at any rate, I had bought a tower along the way. That was the tower. It was a Grassus M46, 46 inches on the face. One section weighed 750 pounds or so. And the guy wire I had acquired over the years, because in the good years, I could buy things and not have to worry about it. And I saw some nice preforms, and I saw 2 big spools of wire, half-inch wire. What kind of wire? I got a sample, I took it home. It was EHS, which I bought at scrap value. And the big preforms were $1.50 or $2 each. I should have bought the whole pile, but I only bought like 150. Little did I know I would use them all. The junkyard also knew I was into collecting boxes, and that's a 300-to-1 big box. It looks small, but this area from there to there is 46 inches. That's a big, big thing. And my chain is an 80, and I discovered there's a big difference between 80 and 80H. H is much stronger. It costs twice as much money, but now it rotates with 80. That's the mast, which was free, public television. They replaced their antenna. They knew I was collecting things, and so I could take that down, and that's what I use for the mast. Those are the elements, and that was the way it was boxed up, and I collect things in boxes, many, many things. There's the boom of the beam, and that's the way they would support the elements, and I looked at that and thought, no way. That'd be good for maybe a 10-meter beam or 6-meter beam, but not 80 meters. And there's a close-up. That's what they had for guying it. It was good cable. It was fairly strand, but the boom, look at the boom. No way. And I thought, what do I do about a boom? I thought I could use a Rowan 25, no. A 45, no. A 55, no. Why? Because over the years, in the good years, when I could scrounge through power company dumpsters, I acquired a lot of U-bolts that were anywhere from 3/8 to 3/4 inch diameter. So this uses big U-bolts on a pie rod tower, which is a solid rod, and you tighten it up and it's good, unlike a tube where when it gets, and it wears out and falls off. Anyway, that's a serious tower. To make sure it was strong enough, I put 100 feet of it together. I have lots of it. And I put 200 pounds on one end, and I'm 175 pounds. I was on the other end. The tractor held up the middle, and it was straight as an arrow. I thought, that'll do for a start. Now, you know, in Finland, the boys put up some really big antennas, and they were red and white. I thought, oh, it went down in a big storm, but I thought, I have to paint them red and white, so I did. Then I needed a mount for the thing. And this mount was created. It weighs 500 pounds. That was one of the hardest things to get up because 500 pounds, you're getting it up, okay, but how do you get it over to the big mast? But anyway, we did it. And there are big U-bolts when it came up that would mount right there. And then whatever area we'd have, we have big steel plates in the center holding it. And this is one of my friends that came out. He did 3 big antennas, the biggest ones, BTs, and that was there. He came to visit me, and he said, Paul, you know, what you really have to do is to put more Philly strand on it, and also under the elements so the wind can't blow it up. And having 3,000 or 4,000 feet of 4,000-pound Philly strand, which I bought cheap, I really beefed it up. Now, I like ways of mounting my antennas like that. I really don't like it where you have little U-bolts, 1/4 inch bolts, and they have them so close together you can't get in. I like a cradle, and this is the big cradle. That cradle weighs 500 pounds. From there to there, the boom sits right through there, and that was a trick to get on, but it's very strong, and the wrench had to have an extension of 4 feet long so I could get the bolts 1 inch tight. And those are Telrex beams, and I have a lot of tower. One time I was coming back from Madison, Wisconsin, depressed because our mission money was cut, and I saw a truck pull the trailer. Oh, what is this? And I waved to them, and they waved back, and I followed them. Instead of driving 70, 75, I was going 45 miles an hour following them. It seemed like 1,000 miles later they stopped. I talked to the person who was driving it. He said they were from, I think, Kentucky. You're going to where? Going to La Crosse, Wisconsin. We're taking down a 400-foot television tower. Taking down a television tower. Is Channel 19 going off the air? No. We put another one up last year, and we have to switch the antennas and take the old one down. If you know anything about me, my question is, what happened to the old one? And I bought most of it for $50 a ton. And one section weighs a half a ton. So I have a lot of that tower. And then I have to finally get a big crane to go up. Oh, this is a test crane, a little crane. And I wanted to find out what the SWR was. On those tower sections, which are about this high, the low frequency was 3.35 because it's close to the ground. What will it be like 50 feet in the air? So the crane lifts it up a ways, and we find out it is in reasonable area. But I thought, for the big crane, we have to have dry weather because one time this truck got stuck out of his mind. One of my church members had this big tractor, and he huffed and puffed and got it out. or it would have been a bulldozer at big expense. And that is the tower. The ladder originally went up the center, you know, on the side. That's a terrible way because you always have buckets going, they get caught, so the ladder is moved to the outside. And again, this is the beam. Next. And now here is the big mast sticking way on top. Actually, I have a 15-foot, could have gone on top of that. And K6 BT said, you know, if you just mount the elements on this tower, it'll change the resonant point. What you have to do is put it in fiberglass. You have to insulate it. Well, so happens over the years, I've acquired 3 chunks, like 3 feet or 4 feet square, 1-inch fiberglass, and I have the tool, and you know what I do. The cost was 0, which the translation is if I would have had to pay for all this, I would be broke. Then K6BT also said you should also cover the coils, so I did that. Put it in the lathe, and I got the holes. Okay, now we're about ready to ascend into the heavens. That's my wind generator. I always wear a red jumpsuit, always, so the people on the ground know the guy in red is 0 AIH. I wish the guys on the ground would have different colors because I don't know, Tim, who's who on the ground from 150 feet, okay? And now we're starting the ascension of this probably 3,200-pound beam. And the ropes steer it up. And off we go. It's coming up with buckets on it so we don't have to carry them. They're steering them around. Next. And it's almost there. There are 3 of us on top. We have one, the fellow in yellow, couldn't see terribly well, but he had a radio, which was very good because with a 225-foot boom, he can't really know at 140 feet how close he is to the tower and how close it is to the mast. Well, anyway, he did it with half an inch at a time. It was perfect. And there we are. And next. Okay. It's now almost ready to sit and go to sleep on its big mount. Next. And there we have our steering ropes. Okay. And, well, why do I have that rope way out there and way out there? Simply because they could steer it around easily. But there's a problem with that because if we just took this rope like that and tied it here, we could pull it, but it would fall down on a guy wire and it might get hooked. And I am paranoid about that because I once did that on a commercial tower. It didn't have preforms, it had just regular, and it got caught. It was my 1,200-foot rope. It was caught like 40 feet out. And if it would have been near the end, no, it was near the middle. So my wife really didn't want to do this, but I hooked high and went down and took it off, and I survived. I'll not do that again. You have to do it the right way. When you have a rope like that, you take it loose, get it to the center, and they give it a yank, and it'll guarantee fall 10 or 15, 20 feet away. So I have to go out there and get that loose and march it back so that my good rope, 1,200-footer, can go down safely. And then I march back again. And those are the tower guys that were there. They were the guys who helped set it up. And that's the person that was with me way back in 1949 when we started amateur radio, 00PQS. He was a very neat Nick, and I inherited some things from him. You always write on boxes what's in it. My place is very well marked, very well labeled. So when I'm SK, if you want something, you look at the box and you can find it. And that's the top, a wood mock-up of the top when we put it up several years ago, and we all signed it. And it hangs in the basement. And those are the fellows that marched. This is my son-in-law, W0UC. This is N9QIP. He's the one that had the drone and did all the drone. There I am in my red jumpsuit. And this is the fellow that operated the radio. And this was another tower person that was just with me to help get the big bolts on. Okay? And then once it was up, I thought, with that big beam, there's a lot of wind load. And though I have 3 guy sets on it, and they're half-inch EHS, and I have one at the top. I also had, these star mounts from years ago. The star mounts, the guy wire, all that I bought for like $300, like 35, 40 years ago. But I sat on it all those years, and now it's in use. And I thought, I'll put that star mount on. But it was hard to put the star mount because they're very heavy wires. That was another story. But at any rate, that is a well-guided tower. And this is the mount. This is it. 1-inch bolts, super strong, not generic bolts, not 3.6 or they're extremely, extremely strong. And I thought, well, my impact wrench, no, forget that, no. It needed a 4-foot extension. And that's it. And if you look very carefully out there at the end, I have a bottom support, has Philly strand that goes out so it can't move around a lot, and it also keeps the wind from blowing it up. And it also has an angle iron mounted on it because the distance from there to there is about 4 feet. And if I got down at 140 feet in the air, I don't know how I'd get back up again. So I have a step. And if something went wrong with the coil and the switch and the relays, I wouldn't hesitate to go out there, step down, tie off, and do that. The W5 that had an OptiBeam that went bad, they had it rebuilt, and I wanted him to send me one of the boxes so I see what kind of relays were in it, but he never sent it. They were rebuilt. Maybe it's because they put in 10 kilowatt. I don't know. Anyway, I don't know really, but it works well. It has 4 segments, 3,500 to, anyway, 3,750, well, 3,700 to 4,000 or 3,000, 4 steps. I wish it would have another step, but hey, 4 isn't too shabby. And this is the bottom of that 300 to 1 gearbox. That's like 2 inches in diameter, and this is another motor that, or Selson, that picks off the direction, and another motor drives that one. And that's the completed thing up there. That's a lot of guying, a lot of Philly strand, a lot of work. And that's how it looks up in the air. Pardon? How long start to finish? It seemed like 10 years. I'll read you a little story my wife wrote. She always writes a Christmas letter, and this is what she said about the beam. It's in yellow. It's probably in here. Oh, okay, here it is, here it is. My wife is a very good writer, and this is what she wrote. Mostly the summer was consumed with the 80-meter beam, which I now call the 80-day except for beam. I don't know exactly how or when it arrived, but it was just an aluminum thing lying out in the field on 2 horizontal towers to keep it off the ground. Well, the boom was quite streamlined, weak and wimpy, so it was replaced with 70 feet of Pyrod 18-inch tower, burly and strong. The elements are droopy, give them Philly strand wire struts. The elements are prone to wind damage, give them bottom struts. The whole thing looks like a spider with a bad case of rheumatoid arthritis. Spent hours, days getting all elements perfectly lined up, perfectly balanced, struts perfectly stretched, paint the loading coil covers with really special paint. Then a big mount is designed and fabricated by a guy smart at commercial construction, known as a big black heavy thing, 480 pounds. Extra 1/2 inch guy wire with eggs are needed, done with the help of a young man strong. Yep, I'm not as strong as I used to be when I was 21. At any rate, then it came crane day. Crane is 125 ton. Ground must be hard, it is. No recent rain, all is well. No obstruction in path. Well, my zinnia flower bed, do you know what 125 tons will do to zinnias? Completely squished. Hams from near and far gather to see the ascent. Smooth as silk, 220-foot boom. We even had a drone operator, N9QIP, do 9 videos with music. It is now on youtube.com, N9QIP. And now comes the except fors. If I and the other guys who were pressed into service as winch operators had a nickel for every time we winched Paul and his helper Jason, who was often aboard, we'd be rich. He was always finished except 4. There were cables and connectors, a star mount, an old chain, then a new chain. Pieces went up one day, would come down the next. The devil, whom I'm sure went up with the beam, sat there laughing and messing up the wires. Many days, Paul would go up and I'd winch him down, and finally, deep dusk. When the rope had to come down, it was wet. I couldn't winch him down because the rope was too wet, but he was finished except 4. He wanted to take a couple more pictures, but I'll have to wait. I'm thankful for answered prayers and the assured help of many angels as he made his way around the tower at 140 feet in the air. And that's the story of the 8-inverted beam and my wife, who has put up with me for 40, well, it will be 64 years, June 12th. And her maiden name is Beach. She does not do well on beaches, does not do well on the ocean, but we're going to, for a celebration, go down on the River Queen, down the Mississippi part way, and celebrate all our years. And she's put up with me, and she's a good winch wench. When we were putting it up, one guy said, oh, you know this? My wife said, look, that's my husband, and I've done this many times. I want to do the winch. She usually doesn't shout at people, but she shouted and said, no, I'm the operator. Good for her. Thank you very much. And thank you for asking me to come.
It doesn't get any better. So have a good year, a safe year on the tower, and we'll see you back here in Xenia in 2018.